Good morning, lovely people. We're going to discuss this rebar right here. This rebar doweled into the wall. When I say doweled, it's just drilled with a smaller hole and they pound it in. It's not epoxied or anything like that. Nothing elaborate like that. Now, I'm not beating on a 1K guy here. You know, he's trying to share his knowledge, right? His knowledge, not knowledge that may be exactly right. I wrote him, no reply back yet. This is last night. I wrote him 9 hours ago. I wrote 1438. The dowel is all but useless. You did not need it because you did not grout the entire area it was in. That's one. You did not grout solid fill the block it was in. It is useless. If you think it is to stop fall from falling, you know, they stop fall. You know, people say, oh, it stops from falling over. You know, of course, it's overturning is what it's called, but people reference it as, contractors reference it as falling. All right. And some of you guys will just say it's gravity. Yep, don't resist the chance to say that. Then you have a footer issue. So if you're worried about it falling over your wall, when I'll show you this wall system, if you're worried about it falling over, you're dealing with your footer issue. Or a loading that's pushing it outward, say a roof line that's not tight, that's not allow all the loads transfer in a downward and outwards position, and then down this way with gravity. All right, footer. This is what I told him: footer, for the conditions and loading expected to take place. So your footer needs to be the size for the load you're expecting, and the size determined by the soil conditions, and the reinforcement determined by the same. I also noticed that no key at footer was used unless you count the roughened water edges, or the roughened concrete. So here is what I'm referencing. This rebar here. Now he just notched out this part of the concrete, which he's doing here, of there. It's just laying there. It looks like no mortar's going on top of that location to even attempt to lock it in. Back here, yeah, it looks like. But he stuck the rebar out here into the webs of the block. Let's hear what he states.
Bar that we have over there in the corner. Let's put on a little bit of mortar on the face here.
All right, so there's his gap, right? Let's do this. There's a gap just created for the rebar to go in, just so it doesn't get lifted up. Well, he's already notched that, and he's notched this, so you know that's significantly notched, and that's significantly notched. So the rebar might be ½ inch, and it looks like the dude's got about, you know, an inch of clearance minimum, but it can be resolved with some concrete there. But what's the intent of that dowel? What is it supposed to do? Stop this wall right here from falling away? Because rebar works in tension. So pull on this rebar, pull on that bad boy, and you've got something falling away. Wait a minute, but he only drilled into there and drove it in. No epoxy, no fancy setting. Just drove it in. So if it was falling away, it would just pull itself out of the wall. Okay. So is the intent to stop the wall from falling in when they do the backfilling? Oh, I see. So now you're using this as a shear bolt as the wall is anchored here as you backfill, that this reinforcement, this ½ inch rebar, stops all this soil at this location. And it takes on the stress. And I guess ultimately when it rushed out, then the wall will just fall inwards from the loading from outside. Oh, I see. You know the way I talk. But that's not mortared in. It's not continuous. And that's not how you stop it anyway in this capacity. You don't stop that overturning with a shear of the shear ability of a piece of rebar. This is the house building wall, if you will. This is that one piece of rebar here, and he'll put another one further up. You stop that overturning by rebar going down and coming all the way up through your block here. And this will stop the tension that's create. It will meet the resistance of this wall this soil trying to push over. Now location would be this side. You can put it in the middle if you want, but this side is more appropriate. This side over here, not this side, not this side for sure. And the middle is just playing it safe. That's your neutral axis, and so you still may get some overturning before the rebar is able to stop it. Again, the rebar goes up in here if you're worried about this soil, not this. All right, let's watch them place it. And this is not a critique of them.
Shake it to get the gravity.
Not a critique.
Then I go down one, shake it again.
Gravity.
And I go down like that.
And there he's placing it. And I watched this entire video. You guys can come look at his channel. And there he is there. And it never gets grouted. This doesn't get solid grouted, nor does rebar go down inside these guys. But there's the existing wall. And right there's that one piece of rebar. What stops that soil? This the weakest point of his soil, but it's also the strongest point. This wall is now butting against there. So it's sections that you would look at it, and also with elevation, surcharge of soil. Is it going to be higher over here? Is it going to be tapered off? How's the water hydraulic pressure on this thing? Is the water going to be down here, or will water just make its way away? All right. Is the soil stable? What is its angle of repose? So real quickly, angle of repose of this soil, as I see over here, it's pretty damn stable. His block is going in right here. And this section here is this section back here. All right. And it's holding pretty firm there, not falling down into his wall system. So your angle of repose is if you take a bunch of rocks and you just drop them on the ground. I did a video on this. Wait a minute. So here's his footer that I talked about. You know, is it keyway? Is it roughened enough to take the block without it sliding over from forces? And I would argue that it would probably need, you know, the dowel is safer, especially since we're looking at well, let's talk about the angle of repose again. You see how close this is, and this soil is so stable. But it appears to be presents as clayish. Clay, upon getting water on it, which I talked about in another video, it will actually draw in more water. It will draw in more water and expand and fracture this wall system. Capable of fracturing this wall system. So here we see cat iron. All right, cat iron. Cat I. Cat I iron. All right, cat iron. Get it? Cat iron. Cat iron. You know I say this stuff to help you remember, like punk shear. All right? Cat iron. A cat on an iron. Cat iron. All right, enough of that. So looking down here at this, you see what is going on. A relative ability of soil to store one particular group or nutrients. All right, so clay soil takes on more water. Its ability to pull water, hold on to, let's go for it, more of the water molecules and expand. It's just not one-to-one. It has an ability to expand, suck it up like a sponge and expand. So you get more than what one-to-one. This soil, this clay has, you know, like a positive negative electrons. It's able to take a water molecules and take it on, and all that soil does it. And when it does that, it expands. Hydraulic pressure is much more, hydraulic being the fluid here, hydraulic pressure, not the soil, not the clay really. The clay is not really doing it. It's the hydraulic pressure, the extra fluid, just like hydraulics in a vehicle, hydraulics in your brakes, etc. And the brake lines are not what caused the problem. It's confined in the brake lines. The soil, if you will, the soil, the what we call clay, is just the brake lines for this expansive hydraulic forces to take place, to maintain, to lock in the fluids, and then when it expands, when the hydraulic fluids expand, they create the hydraulic force to get your walls to move in. So here is what is the highest cation. Remember cation exchange capacity, and this is the clay. It can hold the most. Clay to attract and hold cations because of its chemical structure. All right, you can look this up. And if you search for clay, soils, construction engineering, failure analysis, you'll see my video on this. This wall was pushed in. This was the remedy for that, and an exterior stairs go down, and then you enter into a doorway. There was no door there. That wall was bulged. It was done. At that point, it was an opportunity, right? It was an opportunity. The opportunity, hey, fix this wall, or put another wall here, fix that wall, make this the wall, get rid of the bulge, which is right about here. Get rid of the bulge, make that your doorway, and have steps go down. And you need a sump pump down there, and you enter, and you go there, and that's what they chose. And there's the entrance here. This soil's all back here. This has reinforcement in it, rebar reinforcement, 2 directions.
Okay. So we got the...
As you can see, the reinforcement is lying on the ground here. This has overlapping reinforcement in it all the way up the wall, and solid poured. And I think it's every 3 feet about. And the corner is this butts back to there. So no rebar is needed on the corner. It's going to butt against there. That's a wasted rebar. So you come in and you try to, if you can come in every 16 inches, that's even great. But because now you're interlocking, you got interlocking block. So every 16 on a 16-inch block is perfect. I mean, it's beautiful. Solid filling is not needed at that point. But it depending on how expansive the soil is, and in this case, we agreed that it would go back with a different material, not the clay, would go back a different material here that would allow this clay to expand, hit this other material, this soil that could take some compressive loading from the soil. It's the redundancy factor of it. It could take some compressive loading from the soil, from the clay, when it expands, hit the soil that does not expand when water gets to it. It would compress a bit, and over time, he would just fill it in as it compressed, as you got a void outside here. What the reality was, got this far, I don't feel like buying that soil, money-wise, obviously. So the clay went back in there. Totally not part of the plans and the redundancy factor of the reinforcement. It was the redundancy factor was the soil going back that was not expansive when upon water. It wouldn't expand with water saturation. So here you can see a worker filling in the reinforcement, and it's about every 32 inches. This one is already butted against there, so that's okay. I don't recall if one's in there or not, but there's one here. It's solid filled. That one's solid filled. That That one's getting filled. I don't see any mortar down, so that's there. One here. Oh, that looks solid filled. That one looks solid filled. And he's doing a couple down there. That's what it looks like. Oh, and for clarity, or more detail, this top course has rebar across it, and this one here, the top, so it's these courses here, this will get solid filled, like a bond beam, concrete, all the way across. Oh no, it goes up one more, and then that gets to like a bond beam deal.
Course there.
You can see them loaded.
Some of it sticking above.
Okay, so no, I recall now. Now this is the height. This is the finished height because the soil was here, if I remember right, and then all this gets backfilled. There's something going down here, I think, with the septic, so they need a little bit of special reinforcement to get around all that. There's your footer, how significantly wide it is from this block system. And again, it's overlapping rebar, not just a tall piece of rebar and you slide it over. It's overlapping. So a couple years back, 3 years ago, I did a video, angle of repose. I just posted real quick and threw it up there, and let's see how it goes.
Dude, because basically I did an attack video on lat.
So this is the angle of repose of this stone versus the base versus the height. And the conditions, water or not. As you can see, look at that little valley created. The slippage that takes place also on these tall mounds. Sliding, the shear. And here's a mini one. And it's about the same angle as repose as the larger one. This stone has an angle of repose that looks like that, right? So somewhere about 45 degrees, the stone has an angle of repose. That's the max you can, if you keep piling on top of here, it's going to still keep finding 45 degrees. It will enlarge its base, but it's 45 degrees. And that one's about 45 degrees also. Continue that down a little bit. And that one's about 45 degrees also. I walked up to the stone and looked at it. And that's about 40, well, not quite. That looks like less. So 45 would be probably here. So it's about 40 degrees. And I think I'll walk up. There we go. And so here's the stone up close.
Stones, they're exact.
So these stones, that's what it can hold. That's what it locks in at. Now you go to that clay, and that clay has its own little system altogether of its angle of repose that looks like it's stable, and it can go straight 90 degrees up, right? It just looks that way. And here's the block wall going up, and you got this little bit of a gap, only 16 inches. So it appears that it's stable as can be, until that water gets in there, till the water penetrates, and then this becomes a massive sections of so down here, if you go concrete, cracks, ACI, got it wrong. Angle of repose, concrete design, angular versus round stone. I like round stone. I think angular stone, under stresses, creates a wedge. These are wedges. These are just wedges under compressive loading. There are many wedges everywhere. Round stone, less of a wedge, right? Simple as that. More surface area or more consistency with the surface area. I think this is just cheaper, and they're going to justify why this stone is stronger. Yeah, I know about the compression test and all that. These stones will want to slip past each other. You get a little reduction and compression, but you can get that compression back up with your other mixed designs. This is, to me, is weaker, makes a weaker mix. This has been done in a couple of the major buildings out in Washington, state, the round stone, and it gets some high PSIs. You know, you get your 10,000 PSI. So you're getting your high ratio kips. So coming back to my man's video here, here's where the block is going to be placed. Between that is the where he's got stone, and the angle of repose of the clayish soil as it is. It's damn near parallel with this wall system. It's that thing is like, you know, it's like that. It's like, this is 90 degrees right here. This damn thing can hold at 80 degrees. Once this expansion starts happening from water into it, though, that's a little bit of all bets are off. At the very top, that pin could contribute to help near the end of the wall from rotating in where it meets the house, the structure. It could help if it was locked in, mortared in. But again, what works is the reinforcement going straight up, not not these little dowels. That's not it. That little dowel will get knocked out of position, no problem at all. As you can see here, no more dowels are going in. He's just putting the block there. So it's, you know, it's like I don't know where the dowel is. Dowel there, and they'll put one up here. So there'll be 1, 2, 3, 4. You know, many blocks before you run into that one little small pin that's not engaged 100% with the block there. So let me move on. So this is what it looks like, the perimeter. There's that angle of repose. Hold on. And let me get you some lighting here. There we go. So this looks like it's got a fabric on it. It's protected from rain, perhaps. And your dowels are over here. It's like a dowel here, and maybe one up higher, like I said, up there. Over here, maybe one there. I didn't see them to this side. It appeared to present as this side. They showed the dowels on. But again, the reinforcement inside the block, down into the footer, is the way to go to help with this overturning capability of the soil and expansion. When I say soil, clay. Again, your reinforcement going towards this side to resist the forces is better than having it on this side. Once you think of your spine, this will be a spine. These reinforcement on this side of the wall can bend over. The block, I'm going to open up the block here. Well, let me do this. I'm going to put the block on the back of the spine. So I'm exaggerating, of course, but I want you to see the way the rebar can do that. Now, if the rebar was here and we put the block in and you attempt to bend it, I'm going to put the block on this side of the reinforcement, the structure. You can see that all of this side goes in compression as you try to rotate this spine. The block helps resist also. So this rebar that would be back here trying to rotate by the loads pushing this way would put the spine in the rebar in tension, but also it would have to defeat all the compressive moments here. Whereas the rebar was on this side, let's change colors on that. If it was on this side, it can push it over from the top and the metal would just bend a lot more. Be a lot more pliable. Just think of it on the outside, and it would just open the joints on the opposite side of this wall. Just open them up like the spine here. So placement, rebar, this side for that. Now I have another little trick for you on rebar placement. It won't be in this video. I'll talk about it to you about wall system also, but about in your foundation, your footers. It won't be in this video. I'll give you a teaser. Maybe you guys will catch on. Your footers. Placement of rebar and footers, all right? So placement of rebar and footers. How it's being done wrong today. And for many years. I want you to think about all these walls that are settling. All these walls of all those settlement cracks. It shouldn't be happening. With the proper placement of rebar, when it shouldn't be happening, most of them should not be happening. Most are all of them under the conditions that they saw the soil under. It should not be happening. It should not be. You should not be getting all these cracks. Okay, I'll explain that in a future video. This video was just to help you guys with the reinforcement, the rebar, and educate you on that. Take care. Love you. Bye. Of course, this is not full in depth, but it's pretty damn good, I think.